So we have seen that the concept of entropy is very important at predicting the direction of the arrow of time. But one thing we're not quite sure yet is what really is entropy? What is the molecular or microscopic root of the concept of entropy? Well, it turns out this entropy is deeply rooted in the microscopic picture of the system. It is associated with the so-called degree of disorder. What do I mean by that? Well, we have to understand two different concepts. One is called microscopic state and the other one is called macroscopic state. Okay, when we look at a tank of gas, we're interested in, for example, its temperature, its volume, its pressure. Those are all macroscopic quantities that are specified by these macroscopic parameters, okay, pressure, temperature, whatever. When I say a system is in a certain macroscopic state, what I mean is I can specify its pressure, its temperature, its volume, and so on. Now, for the same macroscopic state, the underlying molecular movement, the underlying molecular states can be far more than just one possibility. Okay, if you can specify the details of the movement of each molecule, then you have established what's called a microscopic state. A microscopic state is far more detailed, contains far more detailed information than a macroscopic state. Okay, to specify a microscopic state, you have to tell me, for example, where each molecule is, how fast is it moving, and so on. Okay, but you know, it is possible to have a certain pressure without knowing exactly where each molecule is. And there's so many different ways to create the same temperature. For example, I can, slow down each molecule, but at the same time, I can give it more molecules so that you can, on average, the temperatures, the pressure is still the same. Okay, or I can make several molecules go faster, several other molecules go slower, so that on average the pressure is still the same, and yet you have just changed the microscopic state. So that tells us that even though the macroscopic state is what we're interested in, each macroscopic state can contain many different microscopic states. Okay, and let's take a look at a simple example. I'm not interested in pressure, temperature, these complicated quantities. I just want to know where a molecule is. And not only do I just want to know where the molecule is, I just want to know something very crude. Okay, I'm going to have, let me imagine I have a chamber. This chamber is being artificially, imaginatively divided into two sides, the left-hand side and right-hand side, with an invisible partition. And let's say I have only two molecules, a red one and a green one. Okay, my question is, where is each molecule? Okay, so I'm not looking at the entire microscopic state. I just want to know one aspect of the microscopic state, and that is where, on which side of the chamber is each molecule. All right, now if I want to know that, these are the four possibilities, right? The red one on the left, green on the right, the green one on the left, red on the right, or they're both on the left or both on the right. There are only four possibilities. Each of them is a distinct microscopic state. Now, you take a look at these four states. You find that 2 out of 4, look at these two, 2 out of 4 features a very uneven distribution, and that is the one side of the chamber is vacuum, has no molecule in it whatsoever. In statistical mechanics, there is a fundamental assumption, and this assumption is that all these microscopic states are equally likely to appear. In other words, the probability of each one of these microscopic states has the same chance, is equal to each other. So each one of them has 25% chance to appear. And out of these four possibilities, 2 of them are totally uneven, with one side totally vacuum. So if you got only 2 molecules in this room, okay, and only 2 molecules, you ask me, what is the probability that half the room is totally empty? Well, it's actually very large. Probability is 50%. Okay, it's 50%, right? But in reality, you don't worry about half the room totally empty when you have no air to breathe, because we have more than 2 molecules, don't we? Okay, so let's look at the trend. If n increases, n is number of molecules. If it increases from 2 to, say, for example, 8. So here is an example of 8 molecules. Okay, 8 molecules. How likely can we find an uneven distribution? Okay, this of course is an example of a totally uneven distribution. This time I use different colors for each molecule again. Okay, different colors. There are 8 molecules, and there is only one. Here is a situation where all these eight molecules on the left side of the chamber, so the right hand side, has no molecules. To make this happen, all the molecules has no choice but to go to this side. Okay, and there is only one microscopic state which will give you this totally uneven distribution with nothing on the right hand side. Right? Of course, is that possible? Yeah, it's possible. But remember, this corresponds to only one microscopic state. Each microscopic state has the same chance of appearing. Now, what if I want an even distribution? So 4 here, 4 there. How many different microscopic states can I draw to make that happen? Well, a whole bunch, right? I mean, here's one possibility, and here's another one, here another, and you can keep on going, keep on going. There are so many of them. Okay, now you can easily count how many of them are there. So how many different ways can I put 4 molecules on one side and 4 other molecules on the other side? Well, basically I have 8 molecules, right? I pick up 4 to put on the left hand side, for example. How many choices do I have? Well, the first molecule I pick, there are 8 choices. The next one has 7 choices, 6 choices, and 5 choices. Okay, so this is how many ways I can take 4 molecules out of 8. But don't worry, don't forget, when you do so, the order that you put in does not matter. You don't say I have to put in the red molecule first and the green molecule second and so on, as long as you get 4 molecules. Okay, so you have to also divide this by the number of ways you put the order. Number of ways you have different orders for these 4 molecules. That's 4 factorial, 4 times 3 times 2 times 1. But even if you divide this off, you do this math, you find there are 70 ways. I only drew 2 of them. There are 68 other ways to do that. So dot, 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 dot. Okay, so this case of 8 molecules. If you want to put everything on the left-hand side, there's only one microscopic state to make that happen. If you want to put 4 on this side, 4 on that side, there are 70 different ways to make this happen. And each of these pictures has the same exact chance of appearing. So how likely is this compared with that? Well, then we say an even distribution with 4 molecules on this side, 4 molecules on that side, it's 70%. It's 70 times more likely than this uneven distribution. Now, when we say a macroscopic state, I only care how many molecules on this side, how many molecules on that side. In other words, the distribution of molecules. Okay, the evenness of the distribution. I don't care which 4 molecules on this side, which 4 molecules on that side. So all these, each one of the 70 is equally good for me. While if you want an uneven distribution, too bad, there is only one possibility to make it happen. So therefore, with 8 molecules, you find you're not going to get 25% chance of having all molecules squeezed on one side. The chance of all molecules squeezed on this side becomes much, much less. In fact, the even distribution is 70 times more likely than totally uneven distribution. Okay, now you get the picture. If this continues, what if I have 10,000 molecules? What's the chance of 10,000 molecules all squeezing on this side? Well, again, no matter how many molecules you have, if you put everything on this side, there's only one microscopic state to make this happen, right? Now here, on that side, 5,000 here, 5,000 there. You're going to need to select 5,000 molecules out of 10,000, put it on this side. How many different ways do we have to do that? Okay, millions of ways to do that. So then we say the chance of an even distribution for 10,000 molecules, 5,000 on this side, 5,000 on that side, is astronomically greater than this totally uneven distribution. Okay? Now, what if I have Avogadro's number, 10 to the 23? Then this even distribution, having an incredibly large number of possible microscopic states, would be far, far, far more likely than this totally uneven distribution. This is why, in practice, you never worry about the fact that the possibility that the oxygen in this room are all going to go to the front side so I can breathe and you're going to suffocate. Because the chance of this happening, even though it's not 0, is astronomically small because of the sheer large number of molecules. Okay, this also tells us how a system can naturally evolve. You know, each of these microscopic states is equally likely, right? So what that means is that if you look at the macroscopic state, okay, you're looking for a macroscopic, say the distribution, the evenness of the distribution, If something starts like this, totally uneven, is it going to stay that way? No, because the system will alternate among all the possible microscopic states, right? It changes very rapidly, right? It will naturally evolve from this case to that case, because after all, that case involves so many different microscopic states. Okay, this explains why entropy allows us to predict the direction in which a system will evolve. Because, again, each microscopic state is equally likely to appear, and therefore the system will naturally evolve into a microscopic state with the greatest possible number of microscopic states. Okay? That's why you go from an uneven distribution to an even distribution, because the even distribution, even for 8 molecules, is 70 times more likely than the uneven one, because it contains 70 microscopic states. Okay, so what is the microscopic nature of entropy? Entropy is related to the number of microscopic states, W. Okay, what's W again? W is the number of microscopic states that's contained in a macroscopic state. Okay, just how many different microscopic ways I can make this happen. All right, I can make this happen. And naturally, the entropy increases because each state is each microscopic state is equally likely to appear. Therefore, the system automatically evolves to have a greater and greater W. Okay, and therefore, that explains why S never decreases, because W keeps on increasing. So the system is automatically going to settle in to a macroscopic state in which W is the greatest. That's where, that's when the entropy becomes the greatest, and that's where the system will end up at. Okay, so microscopically we say entropy is a measurement of the degree of disorder or randomness. Disorder. When I say the system is random or disordered, what does that mean? It means there are so many different microscopic ways to make it happen. Okay? For example, if you look at the distribution of molecules, you got 50% molecules on the left-hand side, 50% of molecules on the right-hand side. That is far more random or far more disordered than to have all the molecules on one side. That will be highly ordered because you know exactly where each molecule is. It must be on the left chamber, right? But with 50-50, you never know, okay? Each molecule has a 50% chance of appearing on the left, 50% chance of appearing on the right. Therefore, the system is more random. So you see, indeed, entropy is a quantity that refers to the randomness or disorderedness of the system, and that also explains why entropy in an isolated system can only increase, because the system always approaches greater number of W, therefore increasing its randomness. Let us use this new concept to revisit an old problem of free expansion that we just discussed. This time we're going to recalculate delta S, but using a totally different approach. You know, you have on the PV diagram, right? PV diagram. You have initial state and final state, right? And the free expansion is not a real line, therefore I'm going to, we imagine, isothermal line to connect it, right? But I can bypass all of this. I can bypass all of this because after all, delta S is just S final as S initial. It has nothing to do with how you get there. I don't even have to imagine an isothermal process, whatever. It just take, you see, S is a function of the state. We never derived this, but here is the formula that we used, that we're going to use. We didn't derive this, but we're going to use this formula. You see, you get the same result. Entropy is a function of the state. It is related to how many microscopic states you have. That's W. How many microscopic states? It's K, the Boltzmann constant, times the natural log of W. Okay, so we are going to simply use that formula to say, okay, that's S final minus X initial, and S initial is KB log W initial, and S final is KB log W final. Okay, when you look at this free expansion problem, the initial and final state, they have the same temperature, right? The only thing truly sets them apart, they have different volume. Now, imagine if you look at a molecule, okay? How many different microscopic states can it assume? Well, if you double the size of the volume in which it can roam. Okay, if you double the volume in which this molecule can move around, don't you double the number of microscopic states? Okay, because you can imagine cutting this this volume into many small pieces, and you can label them piece 1, 2, 3, 4, whatever, and you can say, all right, I found this molecule on the nth piece, therefore that's the location of the molecule. Now, if you double the available volume, don't you double the number of available chambers in which the molecule can stay? Don't you double the number of microscopic states then? And therefore, you can imagine that for each molecule, the number of microscopic states available is proportional to V, is proportional to volume V. Okay, now what about the microscopic states for the entire system? The entire system consisting of n molecules, right? So it's going to be V times V times V times V n times. That's V to the power n. Okay, so therefore W, the number of microscopic states, is equal to a constant times V to the power n. That constant can depend on temperature, pressure, whatever, I don't care. Okay, but that has nothing to do with volume. And in our case, the volume changes, so therefore I'm going to exploit this. I'm going to plug this in here. Okay, I'm going to plug, first of all, log V final, log W final minus log W initial. That's the ratio. Okay, you plug this in, C and C cancels. What do you have? N KB log V final over V initial. N KB, N is the number of molecules, KB is the Boltzmann constant, that equals the number of moles times R. So indeed, we recovered the exact same result as we had before. Except this time, we didn't even bother to connect with our thermal line. We just used, the direct formula for S as a function of state, which is K log W. Finally, let us look at what's called a competition between energy and entropy. A system, when it approaches a certain equilibrium, it has two conflicting personalities, it's got two conflicting tendencies. One is, it wants to lower its energy. But on the other hand, it wants to increase its entropy. Right? Isn't that what you want? You want to lower energy as much as you can. That's why something drops, it falls down because it lowers the energy. But then, a system naturally tends to increase the entropy because entropy in the isolated system never decreases. Okay, but the thing is, these two goals are not always in agreement with each other. In fact, they are conflicting goals. Okay, and the question is, which one is more important? And how does nature strike a balance between these two? To understand this, we need to introduce a concept called the free energy. The free energy is defined as E minus Ts. E is the energy of the system, T is the temperature, S is the entropy. Okay, it turns out the two conflicting tendencies can be united in this expression of free energy. In order for the system to reach the optimum state, it turns out that F, it is not E that has to be minimized, it is not S that has to be maximized, but rather it is the whole thing F that has to be minimized. You want to make F as low as possible, the free energy. Okay, now suppose the temperature is very high. What did that tell you? It tells you, okay, you have a negative sign, right? You have a negative sign with very large T. Okay, what do you think? What should we do to make F as low as possible? Is to increase S, right? Because look, this is a negative sign, and T is very large, so by increasing S, you can dramatically lower the free energy, right? So the priority becomes to increase S. But at very low temperature, S is not very important because T is almost equal to 0, right? So the second term is not very important. So how do you lower the free energy? Is to lower the energy of the system. Okay, so where do they strike a balance between these two conflicting goals? Depends on temperature. At high temperature, entropy is more important. At low temperature, energy is more important. This is exactly what happens in the two-level system. At very low temperature, T approaches 0. Everybody goes downstairs because they want to save energy. Okay? Now gradually as you increase the temperature, you find more particles go up. Even though that doesn't save energy, it will increase entropy or the randomness, so it wants to do that. When the temperature approaches positive infinity, what happens? 50% of particles down, 50% particles up, according to the Boltzmann distribution. This is when you have the largest value of possible entropy, because as random as possible, 50% up, 50% down, and yet energy is not the lowest. So that's when you increase entropy.